Hello everyone, my name is Arvind Raja. I'm pursuing BTech in IIT Roorkee. I'm doing engineering physics, and this is my CWS project for the course Fundamentals of AI and ML. So the project I worked on was a RAG-based physics research assistant. So what is RAG? So RAG stands for Retrieval Augmented Generation. So RAG is a technique that combines information retrieval from a supplied data set or a PDF or a web page. So basically anything that contains data. And what it does is it retrieves data based on the query you ask it, and then it works with an LLM. So it sends the retrieved data to an LLM for an augmented generation, as in I would extract raw data from the data source which I'm provided with, and then it would give an augmented reply to my needs with the help of an LLM. So I would supply it with an external knowledge base, which is my data source. So which can be collected through my through documents, PDFs, or web pages, etc. And then it sends it to an LLM for further processing. So this slide is about RAG versus a basic chain. So basic chain is the first image. So there's a prompt, which could be our query, which I'll pass to a model. And this model will process the query and then give us an output. So this is how a general basic chain or an LLM would work. All right. But how does this differ from RAG? So in RAG, the user asks the retriever a question. So this retriever, based on the semantics of the question, it kind of selects certain parts, a certain data, a certain chunk from the data source. In our case, this is a PDF or a document. And then it would select semantically related chunks or data, you can say. And then it would pass on to the LLM. Now the LLM would process this data along with your query, and then it would answer to your query. So why RAG? So if you think about it, we already have an LLM. So why even RAG? The fundamental problem with LLMs are hallucinations. So what happens is, you would have encountered this as well. Let's say you are typing something in ChatGPT or Gemini, for that matter, and sometimes it would give something, and when you ask to cite the source, it would most probably cite the source, but when you go and check the source, it's not what you would expect after reading from the ChatGPT answer. So this is hallucination. So uh, to prevent this, uh, uh, we came up with RAG. So what RAG does is it takes a source, you have the source, and then you would ask a query. So now it would stick to the contents of your source. It wouldn't go outside. So it might happen in LLMs. The other possible scenario is you ask something and then it gives the source, and the source is there, but the source is not very, it's not very trustworthy worthy source. Okay, it could be something, it could be a website, but there is no clear-cut logic as to why this is true, but there is no more explanation, and you don't find it anywhere else. But the LLM would answer confidently. But in case of RAG, this is the data source we supply, okay, our PDF, the book we supply. So if we are confident about our data source, the query and the answer which we get would be pretty relevant. So how does this RAG work? So firstly, let's for an example, I'll take a PDF. Okay, so I'm supplying my RAG with PDF. So the first step is the retrieval stage. So what I would do is I would extract data. Now let's take a standard PDF, maybe a textbook or a research paper. It would have all sorts of data. It would have textual data, it would have imagery data, it would have tables, it would have some sort of more references, right? Sometimes PDFs might even have hyperlinks. So the very first step for you is to organize this data. You don't want the image to be mixed up with the text and be treated as noise. You want to, choose your data. You want to segregate your data in terms of text, images, hyperlinks, references, or table, and then you want to process them differently. So that is the first and foremost step you want to do. You want to do your text extraction, but you want to be mindful of the type of extraction you're going to do. Text separately, images separately. You have to treat them separately, and you have to consider them as well. Like it shouldn't be a case where you completely ignore your image. And the second step is chunking. Okay, so suppose you have a whole PDF. Uh, all right, let's take a book for an example. A book, it's broken into a bunch of chapters. Similar to that, I would take a PDF, or I would take even a paragraph for that matter, and I would break it into chunks. Chunks would be bunch of words with similar meaning, I can say, because most often in language, similar words are grouped together, or similar sentences are grouped together for that matter. So a chunk is basically a bunch of words. You would set the limit. You would set the number of words as the chunk limit, and you would break the entire PDF into a bunch of chunks. Now, there is no necessary condition for these chunks to be independent. It might happen, for example, let's say you have two paras, you have para 1 and para 2. And there's often some sort of similarity between para 1 and para 2. All right. So instead of considering para 1 to be a chunk and para 2 to be a chunk, you can consider the first three lines of a para to be chunk 1, and probably the fourth line. And let's say the para 1 ends in four lines. So para 1 with the fourth line of para 1. And then the first line of para 2 and the second line of para 2 together to be the chunk 3. Okay, so my point is your chunks can have an overlap, and you could set an overlap limit to it. It's solely based on the type of RAG you are building. Okay, it's totally in your control. I had set a limit of overlap limit of about 80, I think. When we are checking the code, I will show that to you. And embedding. So in the LLM model, uh, how it works is basically so there's a lot of linear algebra going on, right? So we would take words would be converted to vectors, and sentences would be also converted to vectors, and you would use a similarity. Similar to that, the words which you're supplying would be converted to a fixed length numerical vector. Okay, it could be 384 to 776. In our case, we are doing the 384 dimensions. So the point of converting to the vector will be very clear when I'm discussing further. So this embedding, it encodes semantic meaning in mathematical form. Why? To find similarity. So basically an LLM or RAG for that matter really doesn't understand your text. We are trying to find similarities and we are simulating an understanding. So we would convert it into a vector, an embedding, and then based off on similar embeddings would be grouped together. So there are metrics, distance metrics, like the cosine index or even the L2 norm, L2 distance, through which you can group similar vectors together. And similar vectors would also mean similar meaning. Similar meaning would, be a correlation. So some sort of correlation, and that's something which we want to exploit. Okay, so in Drag, we embed document chunks and queries into the same space so we can find relevant chunks via vector similarity. This will be really clear now. Yeah. So the very next step is indexing. So suppose you have vectors and you want to group similar vectors together. If I have a bunch of vectors and I'm just, if I have a bunch of data and there's no sort of correlation, it's not really very helpful, right? So what I would do is I would index this vectors based on their semantic similarity. This is a very crucial step for you to find answers to queries. Okay, so based off on different questions, we have based off on different metrics, we have ways to find similarity. So after that similarity, we would choose the top k vectors based off on the similarity, and we would pass it on to an LLM for an augmented response. So this diagram explains it pretty clearly. So there's a question, and this question I would pass it on to the RAG, and there's also a document. Both of them will lie on the similar embedding space. Okay, so there is your vector in XYZ and XYZ. So suppose you have a question, that's marked in the yellow XYZ brackets. Okay. So now you would find vectors or embeddings of the PDF or of the data source within the similar proximity to find an answer. So basically, let's say you have a question and an answer would be semantically related to it. So that is what we're trying to find here. So we have one vector, we're trying to find other vectors or embeddings for that matter that are similar to our question vector. After that, we'll pass it on. After finding that particular answer vector or chunk vector, we would pass it on to an LLM for an augmented reply. So what we used here was the L2 distance. So the L2 distance formula is given here on the screen. So basically, I would have the components of the vector, right? In our case, it was what, 384. So each vector has 384 dimensions, correct? So this subscript would run from I is equal to 1 to 384, where I would subtract all possible uh, axes or dimensions. Sorry, not axis, not the right word, dimensions and dimensional vectors to find the distance. So based off on this, the Fair's embedding works. All right. So the smallest distance means two vectors are quite close, or the closest. So closest means the closest in semantic meaning as well, because in your embedding, each word would be embedded in a way such that similar words are grouped close together in this vector space. So smaller L2 distance means more similar meaning. And for this part, I had used the LLM part I had used was DeepSeek R1, 1.5 million parameters. And the part over here was I had specifically tuned it for the solid state physics data using low rank adaptation. So low rank adaptation is basically I wouldn't let's say an LLM. An LLM has layers and each layer has weights associated with it. So instead of tuning all possible weights, instead of tuning all the 1.5 billion parameters, I would tune specific parameters that are very relevant for my solid state physics data. In this way, I'm my tuning process is much faster, and also I'm getting much relevant answers. I need not tune for other parameters. If I'm making one for solid state physics, I don't need it to match even for fluid mechanics. So that was the reasoning here. So I'll quickly show you the code. Yeah, here's the code. Oh, okay. And another thing over here was I had tuned it specifically for solid state physics. In the results section, I would discuss that RAG, although is quite helpful in this matter, one place where it gets a hit is that it faces a huge hit is that its reasoning is not as good as that of an LLM. It's obvious. You have 1.5 billion parameters here. Normal chat GPT or DeepSeek for that matter would have billions and millions of parameters, and obviously their reasoning would be much better, and they are connected to the internet. The main innovation over here was I was trying to make a completely offline model, although I'm running at Kaggle here because my computer is not second. I was facing some CPU related issues, so I thought of running it on Kaggle. Yeah. So firstly, I installed the transformers library. And okay, before going to this part, I think yeah. So I installed all the necessary packages. The fares, if you remember, was for the vector storage part. So I used the Hugging Face library to pull the DeepSeek R1 distill model, and then I fine-tuned it. So I'll explain till the I had run the cells in different orders, so I'll just show you the parts where okay, here. Here is the embedding model which I had chosen. So this works on the BERT transformer model, and then the vector size as well. The vector dimensions for this model is around 384. Yeah, the dimensions are 384. So yeah, this is what I was talking about. The chunk overlap words where you can, you can decide the chunk overlap words. So I had set the chunk overlap words to be 80, and each chunk of mine would have around 400 vectors, 400 words, sorry, and the top k is equal to 5. That means I would choose the top 5 relevant chunks. Suppose I were to make a query, okay? If I'm going to make a query, I would choose the top 5 relevant chunks based for my query, based on the context, based on the L2 distance. And then I would send it to an LLM, and the LLM would do the processing, and I would get an augmented generated textual response, which would cater to my needs. Okay, so here is where I'm extracting the PDF. Keep in mind this version is not the fine-tuned version. It's simply the distilled 1.5 billion parameters. I'll show the fine-tuning part as well. So this should just shows that I'm running it on the GPU. And this is where I've uploaded my file. This is the file based on which I'll be asking questions. So yeah, here. So here I'm extracting data from, so if you see, I'm extracting textual data differently. I'm extracting the images separately, and also the tabular data. Yeah, so in case if I do not find, where's the yeah, here. So detects multiple tabs in the tabular data. This is how I would detect the tabular data. And in case I don't find the file location, it will throw an error. So if you're gonna run this on the same directory, if you're gonna run this, make sure it's on the same directory. And this is about the chunks where I would so the chunks were based on words. Remember, it was around eight. It was around 400 words with an overlap. So I had used string functions in Python to cater to that need. Like I said, it's similar to the BERT model. Here is a generator, load generator model from which I am generating from the tuned one. So, okay, so the tuned one goes here. Yeah, so basically I'm storing the LoRa adapters in this directory. I'm training. So I had specifically trained it for with the data I had. The data I had was basically question and answer data. So what I would do is it would be a JSON file. I think I would have the JSON file here. Wait. Yeah, something like this, some sort of JSON file like this, in which I would have the question and I would have the answer. So I was fine tuning for the LLM to improve the context between question and answer for specific solid state data. Mm. Um, yeah. So yeah, I had run around 376 epochs, and yes, the LoRa adapters were saved. Yes. So yeah, here I would load the adapters from my path, and then I would combine it with the DeepSeek model which I had downloaded. Another thing I want to talk about is the token length, which would limit the answer size. Okay, here it's just if I want to characters. So, a quick demonstration. So, yeah, this is the question I had said before. What happens on increasing the magnetic field? I uh, had uploaded a PDF based off on solid state physics. It was on cryogenic thermometry. It was about MCD spectroscope, how you can make an MCD spectroscopy based thermometers. And quickly hit on. So yeah, it's extracting the text. That will take some time to load. Yeah, so these are the top five chunks. It's not in a very friendly manner, as in a sense, as in a very readable friendly answer. As in, see, this is rank one, rank two, rank three, and rank four, and rank five. So I have ranked it in terms of context. This, in terms of vector space, if I were to talk about this, it has the closest distance to our query. This is the second closest distance, the third closest distance, and so on. So here from the context provided, so this is the answer, and it also gives the uh, document numbers, so it's in a way it's also citing your sources. So it's quite helpful in that sense. So basically, the answer which we would require for that was when uh, the question was increasing magnetic field. I'll show the PDF. Yeah, between Zeeman level increases. So this was the answer. And what is the answer we did get? Decrease in temperature sensitivity and broader Zeeman gaps. So the reason for the decrease in temperature sensitivity was the broader Zeeman gaps. So in our case, it's fairly accurate. The results part. Yeah, so one thing which I observed was this RAG model is quite accurate for factual data. But if you were to ask a logical data as to uh, infer something from your given data, it has a little bit hiccups. But if it's logical reasoning that's very closely related to your factual data, as in the PDF has nudges, and it's slightly mentioned it somewhere, or you can infer it upon reading from there without much difficulty, your the RAG model works fairly well. So I theorize that it could be used much in solid state physics and material characterizations, where you have loads and loads of uh, factual data, but but in fields like fluid mechanics, where which is like heavily mathematical, or even electrodynamics for that matter, it would face a lot of hiccups. But for fields which have factual data, RAG would work fairly well. Also, it could be extrapolated beyond physics. Like, for example, in chemistry, you can use it in inorganic chemistry, or a really good application of this would be history, where you can upload a PDF, and you can get factual data based on dates or events. So this would be really helpful in the field of archaeology or history. Though it can be used in fields of physics as well, like material characterization. So that was my project. As future scope, you could also uh, tune the retriever such that it can choose the best, choose chunks based on context more efficiently, and the best chunks. So that could be done as well. That could be done as a future work. So yeah, that's basically my project. Yeah, thank you.